Okay, so this is the second in my series of A-level physics questions and topics you should be able to do in your sleep or back to front, because they come up all the time and they're pretty formulaic. And this is about EMF and internal resistance, which a lot of people do not like as a topic. So the thing to say about this is that most questions will tell you to ignore internal resistance, but if you get a question where you can't ignore it, obviously you have to know a little bit about it. Now, internal resistance is something that every single cell or power source has, because every single cell or power source is made of stuff. It's made of wires, it's made of metal, it's made of chemicals, and that stuff has got a resistance in it. So in a perfect world, when a electron travels through a cell, it would get given energy. And it would get given, let's say, 6 joules of energy per coulomb of electrons. And it would use all of that 6 joules of energy in the external circuit. It would have, it could use all of that energy for things outside the battery. However, in real life, it actually takes a little bit of energy for the electrons to get through the battery. So although they're given 6 joules of energy per coulomb, it might take them maybe half a joule to get through the battery. There's many analogies I could make about this, but one, for example, is going to work. So you go to work and maybe you get paid £100 a day. In an ideal world, you would have all of that money to spend on whatever you wanted. But what actually might happen is that it might cost you £2 a day in bus fare to get to work. So although you're earning £100, you're actually only getting £98 net value, because £2 of that is on bus fare. It's the same kind of idea here. You might get 100 joules, but 2 joules is used up working against the internal resistance of the battery. Now, we need to be able to identify different terms and different parts of this circuit. So this is a common circuit to show the internal resistance of a cell. And very often you'll get a little dotted box like this drawn around the cell and this little r. And this little r stands for the internal resistance of a cell or power supply, or EMF source, okay? So this is the internal resistance of the cell. It's not a little resistor in the cell, it's representing all the resistance of the wires, the chemicals, the metals, the materials that make up the cell. So if we think about this whole thing as the cell, then what we could do is I can put a voltmeter across the whole cell. And this voltmeter is going to read the net gain in voltage as an electron passes through, or a coulomb of electrons passes through the cell. And that net gain in voltage is called the terminal PD, and it has the symbol, I'm going to do it in a box, do them all in a box, V, okay? The terminal PD is the net gain in voltage as a coulomb of energy coulomb of electrons, I should say, passes through a cell, and it has the symbol V. The internal resistance of the cell has got the symbol, as you can see there, little r, and that's to distinguish against big R, and big R here is the external resistance of the circuit. Now that could be just one resistor, but it could be a network of resistors and components. But what we do is we simplify them all down to one equivalent overall resistance to make our life a little bit easier. So R is the external resistance of the circuit, R. And then we're missing one thing, and that is EMF. And what I'm going to do here, I'm going to draw 2 pretend voltmeters. So these voltmeters in yellow are pretend. You can't actually get a voltmeter around just this cell and around just this internal resistance, but it's to try and illustrate a point, okay? This here is a voltmeter around the EMF, the power source of the circuit. And in my head, that is the perfect voltage. That's how I often think about it, what I would get in a perfect world. The definition of EMF is the energy transferred per unit charge when transferring from something to electrical energy. That's the definition. This is the description, okay? I like to use the idea of a perfect voltage. It's how much energy each coulomb of charge is given overall. So it's not a net gain, it's like kind of like the total pay. And then here, we've got lost volts. That's what this stands for. annoyingly, it doesn't have a symbol. The symbol for EMF is either E or curly E. I like to use curly E personally. It's been a long day. Lost volts here. I had a real panic then. I thought my video wasn't recording, but it does appear to be. Lost volts is the volts lost or voltage lost due to the internal resistance of the cell. So it's how much energy is used up essentially getting through the cell. And it doesn't have a symbol. One more thing to say, I'm going to draw this in this colour again, I'm going to go back to V, is if I did a voltmeter around this resistor here, these would both equal the same thing, because the net gain in voltage across the cell is what will then be taken away through the external circuit. So these two are measuring the same. So what we need to now do is try and like put these things together. So I'm going to make a sum. I'm going to say that the EMF, actually no, I'm going to do it in a different way to normal. I'm going to say the net gain in voltage, the terminal PD, which is the net gain in voltage, terminal PD, is going to equal the EMF, which is the perfect voltage, minus the lost volts. So the overall net gain is going to be what the battery gives and then how much it takes the battery to get through the battery. So let's say it's a 6-volt battery, but 1 volt is lost as you go through the battery. That means the terminal PD is 5. So the net gain is the total minus anything that you lose. Now we usually write this differently. We usually write it in a different order. We write it as EMF equals terminal PD plus lost volts. So I'm gonna, this is not wrong. I don't want to cross it out because it's wrong. I'm going to put in a little bracket because this is how we normally do it. All I've done is just rearrange that equation. EMF equals terminal PD plus lost volts. And each of these terms are voltages, because if I'm adding terms together, they all have to have the same unit. They're all types of voltage. Now I can write this out in many, many different ways. I can write EMF, E, equals terminal PD, V, plus lost volts. But if I draw a little arrow on this circuit, I, this is a series circuit, R in series. And I can use Ohm's law, V equals IR, and apply it to the individual components. Because it's a series circuit, the current is going to be the same everywhere, to change how I write these things. So I can write instead E equals V plus I little r, where I is the current through the circuit and R is the internal resistance. Or I can go another step further and write the EMF equals I big R, because the terminal PD, remember, is the voltage across the whole cell or across the external resistance, and that's going to equal I times big R plus I little r. Or if I want to, I can then write that as I R plus R. So these are all the different equations you can use, and the different equations that we're going to be using in the questions later. This is probably the most common one to kind of use for theory. E equals V plus IR. If you're doing the core practical and things like that, this is what will come up, and we'll look at that in a moment. Have a think about what happens to terminal PD as I increase current. So I shouldn't have written that there because it's now in the way. But I'm going to come up to here. I'm going to start working up here. So we've got E equals V plus IR. Now, over a short period of time, like, you know, an experiment, two things in this will stay constant, and that is the EMF and the internal resistance. You do actually find that the internal resistance can increase over time, but that's over a long time, not for like one experiment. So EMF and internal resistance are kind of constants for the circuit. And in a circuit, what we can do is we can vary current by varying external resistance. So if I increase the current, if V plus IR has to always equal the same value EMF, then IR will get bigger if I increase current, and therefore terminal PD decreases. So the larger the current, we have more lost volts, and so a smaller terminal PD. Okay, so the higher the current, the more problems we get from internal resistance, the more lost volts, and then the smaller the terminal PD. But this also kind of works in the reverse way. Have a think about, what if there's zero current? Okay, what if the current was zero? What could I say about this equation here? Well, if I equals 0, I get that E equals V. Okay, so another way of defining EMF is the reading on a voltmeter, or we can say the terminal PD, when the current in a circuit equals 0. So when there's no current running through the battery, then there's no energy being lost due to the internal resistance, because it needs a current to lose energy. So one way I can work out what the internal resistance, what the EMF of a battery is to put a voltmeter around it when there's no current running through it, just when it as a separate part of a circuit. And then I will get the terminal PD reading. So the final thing to just quickly talk about for EMF internal resistance is start again. It's been a very, very long day. Is an experiment to work out what the internal resistance and EMF of a circuit is. Now we use exactly the same circuit that we had before. We have our cell with our internal resistance, which I'm going to draw as a little dotty square around as well. But what I'm going to do is I'm going to add in a variable resistor. Okay, and it could be a rheostat, it could be one of those ones you twist it. And I'm going to also add in, because I'm going to measure the current, an ammeter. And I'm going to add in also a voltmeter. And that voltmeter could go either across the terminal PD, across the resistor here, or it could go across the battery, because they will have the same voltage reading, because whatever I gain here, I have to lose here. Now this is quite a different experiment to normal, because usually in electricity experiments we change voltage to vary current. But what I'm going to do here is I'm going to vary the resistance, and that will then change the current. Okay, and we know back from this equation here that if I change the current, I'm also going to change the terminal PD. Normally I would change the power supply, but I don't want to do that here because I'm looking at the internal resistance of a cell. And if I change the cell, then I've changed the internal resistance of it. So I need to keep that constant. So I need to keep the same cell. So I vary resistance to change I, and this therefore changes the terminal PDV. So I draw a table. I draw a table of I and V. I vary I by varying the resistance. I measure the current through the ammeter, on the ammeter, and the voltmeter reading for the voltage, and I get lots and lots of readings, at least 10, 12 readings. Because normally what I'd do is if a normal experiment, I would repeat the same thing a couple of times. I'd do the same reading 3 times and see if there's an anomaly. Here, because this is a variable resistor, which doesn't usually have like a scale on it, you're twisting it or you're sliding it, it's really hard to get repeats. So instead we do lots of readings so we can easily identify anomalies on the graph. So I get lots of currents, I get lots of terminal PDs, and then I plot a graph of current versus terminal PD. And that graph will look like this. Okay, because as I increase the current, the terminal PD decreases, which is something we looked at here. As you increase the current, you decrease the terminal PD. Now what I can do is I can work out what this equation, what this line can do to help us work out the EMF and the internal resistance. Now, any straight line will be in the form of y equals mx plus c. But here, I've got that y is v and x equals I plus c. So I can say v equals mi plus c, and I'm going to compare that to an equation that I've already seen, which is E equals v plus I r. Now thinking about it the other way around, I've got v is y and I is x. So I want to get this equation into this format, and to do that I need to move IR over. So I'm going to write v equals, I'm going to write it down here, v equals E minus IR, but this isn't quite in the format of v equals mi plus c. I've got something minus IR. So I'm going to just rearrange this and write v equals minus r times I plus E. It's the same equation, I've just tried to get it into the format v equals mi plus c. And from that I can compare these two. and I can get this. I can get that the gradient is minus r and that the intercept is e. So the y-intercept there is e, and the gradient equals minus r, because it's a negative gradient, so you need to negative it again to get the resistance. So that's the theory. It's quite a tricky topic to explain, as you can probably tell, but we're now going to do some questions. So the next video is all about looking at some questions, so move on to that one when you're ready.